hopefully he will reconnect. But let us start. So Kusima, tell me, what have you been studying about chemistry lately? What have you been studying lately? Unmute your volume and speak.
So I've been learning about water.
Water. Could you take me through just a little bit what you've understood about water? Just briefly.
Okay. Water has a chemical formula of H2O with two elements, hydrogen and oxygen.
Very good. What else?
I also learned about chemical test for water.
What is the chemical test for water?
Chemical test for water is the testing of the presence of water in compound.
Very good. What do we use?
Anhydrous copper 2 sulfate powder and anhydrous cobalt 2 chloride.
Can you tell me the color changes of those two compounds once they come into contact with water?
For anhydrous copper 2 sulfate powder, a blue solid turns into pink crystals of hydrated cobalt chloride, 2 chloride.
Okay, that is for cobalt. What about for the chloride?
The white powder of anhydrous copper 2 sulfate turns into blue crystals of hydrated copper 2 sulfate.
Okay, so copper 2 turns to blue once it is hydrated. That's nice. Very good. Is there any other thing you'd love to share?
No, sir.
Okay. Well done. So today we shall look at oxygen. And if you have questions about water, please, you can always inbox me on WhatsApp and I answer them, okay? Yeah, or any other thing. So today let's look at oxygen. Have you studied about oxygen?
No, sir.
Do you know anything about oxygen?
No.
Okay. So today is what we shall concentrate on. Let me try to share screen and we see how to go about it. Okay. Can you see my screen?
Yes, sir.
Okay, good. So this is just to welcome you again and hoping that Also, your friends who watch this audio, this video, will see that we are very, very happy to have them. They'll subscribe to Yaaka for the rest of the year. So today's topic is oxygen. If it comes to your attention that you can't hear me well, you tell me, okay?
Yes.
Okay. So we're going to look at oxygen, and what do you know about the use of oxygen in human beings?
Oxygen com combines with hemoglobin to produce oxyhemoglobin that helps with transference of energy in the body.
That is very correct. It is what we use in respiration. Like you have explained, it combines with the hemoglobin and it is transferred all over the body, and it helps in the breaking down of the food that we eat. Now, here is the occurrence of oxygen. Occurrence means where oxygen can be found in nature. So it makes up 21% of air, and it occurs in combined states also, for example, in oxides, in sulfates, carbonates, nitrates, etc. And it is very, very widely spread in chemicals, clay mineral compounds, and others. It's also found in certain food substances like carbohydrates, fats, proteins, and also water. Like Kusima, you were saying that water contains hydrogen and oxygen, which is true. We also find oxygen atoms in water. The picture below shows some of the ways oxygen affects nature. When we have oxygen, in water bodies, we see that organisms like algae survive, fish can breathe, and many other things. When it is very low, for example, in this first picture where I'm pointing here, it is very low, and you can see we only have a few aquatic plants, meaning fish won't have enough food, the algae won't grow well, and things like that. When we have low oxygen, such things are common. But when you look at this next picture, it shows you that we are adding oxygen into the water body, hence we are having aquatic plants grow. Okay, we're seeing organisms surviving better, right? And the sedimentation is decreased. As you can see here, it was a lot. Here it is very low because now we have organisms surviving. They are not dying to form all those sediments. So that is some of the importances of oxygen in this regard. Here we see that in most environments that human beings live, we see the integration of nature and artificial things like these buildings and what. The nature here is the trees, and they help provide us with the oxygen that make sure that the people who are living in these flats and whatever can survive. Plants are some of the organisms that provide us with the oxygen that we need for respiration, like Michael mentioned. In nature, it exists as a diatomic molecule. Who knows the meaning of the word diatomic? Diatomic molecule. You can just speak.
Two atoms acting as one.
Yes. It's combined, right? So
Yes.
oxygen exists as a diatomic molecule. And you can see here, this is one atom, this is the second atom. So two atoms make up oxygen, two oxygen atoms. And that's how it exists in nature, in the atmosphere. In other compounds, you'll find it when it is one atom or two atoms or five atoms, but this is just how it exists in nature. For example, in water, you find that one molecule of water will only contain one oxygen atom and two hydrogen atoms. But when you look at a sulfate, it will have over 4 atoms of oxygen. So it varies, but in nature, it is just only and only 2 atoms. Let's look at the laboratory preparation of oxygen. So far, do you have any questions about that?
No, sir.
Okay, we can continue. All right, so laboratory preparation of oxygen. Here we're looking at how we can make oxygen in the laboratory. Mainly, how we make oxygen in the laboratory, it is just using compounds that are high or that are rich in oxygen. So these compounds have oxygen atoms in them, and what we do in the laboratory is just to separate out the oxygen atoms that we can use to make oxygen as a molecule that can exist on its own. So the examples of those compounds, we have hydrogen peroxide, potassium chlorate, potassium manganate, and sodium peroxide. Those are compounds that really contain a lot of oxygen that we can extract out and use it in other instances after it has been made. But on a large scale, oxygen is prepared by electrolysis of sodium hydroxide and fractional distillation of liquid air. We shall look at fractional distillation of liquid air later, but we shall not look at electrolysis of sodium hydroxide now. That will come in the later topics. Okay, this is how we prepare our oxygen in the laboratory using hydrogen peroxide. So we have manganese oxide, which acts as our catalyst to break down the hydrogen peroxide. The hydrogen peroxide, which is here in the dropping funnel. Oxygen is collected over water. Since it does not, it is just slightly soluble in water, so we shall collect a lot of it here. So what you do, you have a round bottom flask, no heating is required here. In there, you have your manganese 4 oxide. And then in the funnel, you have hydrogen peroxide. You have a tap here that you open, and then the hydrogen peroxide finds the manganese 4 oxide in here. Yes, please?
But on the diagram, it's saying manganese dioxide.
Okay, yeah. The other name for manganese 4 oxide is manganese dioxide. You'll see the formula later. Probably you understand that. This one just shows the valency of oxygen. The dye shows the valence of oxygen in the compound manganese 4 oxide. When I say 4, I am representing the valence of manganese in this compound, not the valency of oxygen. Is that okay? Does that make sense to you?
Yes.
Yes, so when I say manganese 4 oxide, the 4 is a representative of the valency of manganese in this compound. When I say manganese dioxide, the di here is representing the oxidation state or the valence of oxygen in the compound. So for me, I like to always mention manganese 4 oxide to remind me that, oh, The valence here I'm going to use for manganese is 4 to write this compound. And that helps a lot when you're writing chemical formula. You should also try to use it. Good question though, good observation. So this is the diagram. When the oxygen is made, it travels through this delivery tube to be collected over water here. So you see bubbles that come up and then pop on top, and then up here we shall have our oxygen. Do you have any questions on that? Any other questions?
Excuse me, sir.
Yes, please.
The compound in the beaker, is it also water?
Sorry. Here, this. Do you mean this one here or this one?
Where they are collecting oxygen from?
Oh, okay. So this is all water. Here there is water, and then here there is water. Okay, this is all water. This is a trough, and then this is an inverted gas jar. This.
Yes.
Okay. This here is an inverted gas jar. Okay, and then this here is a trough where water is. So the water in the gas jar is the same water that is here in the beaker of trough.
Okay.
Okay. Yeah, it's the same. I should have represented here with water also, because there is water in here. Since it's just an inverted gas jar. You see that?
Yes.
Okay, good. All right. Any other questions?
No.
Okay, we can continue then. So here is the equation for our reaction. We have hydrogen peroxide and a catalyst manganese. Now you see here, we represent it. I represented it in the brackets, the valence of manganese. Okay, this is 4. So can you see this? This is a 4 here, not so?
Yes.
Yeah. Now I represented it to show you the valence. So manganese 4 oxide is our catalyst, and the product we are forming, of course, it is oxygen. Okay, we have oxygen, and then we have water as a byproduct. This water here, it is not the same water that you saw the other side. Let me go back a little bit and show you what I mean. The water formed, it is not the same water here. That water remains in here. That water that is formed in the equation you have seen remains here in the round bottom flask. Okay, it does not go to the next phase. This water here is just a collection method. It is, we just put it on the side. It has nothing to do with our reaction. To go this side. Okay. So that is our word equation, and then the symbols are here. That's the symbol equation. We have hydrogen peroxide still reacting with, being decomposed using this catalyst, manganese oxide, to form oxygen and water. Okay. All right, let me remove these annotations, and then we can continue. All right. Let's look at the chemical test for water. I mean for oxygen. And now water has caught my mind. The chemical test for oxygen. So here, the chemical test, what we use is a glowing splint, which relights once it is dipped in a gas jar containing oxygen. Now, this is what we mean. You might ask what a glowing splint is. This is it. So, for example, you light your matchbox. After it has burnt a little bit, you blow the flame off. Okay. What remains is what we call a glowing splint, which is right here. Okay. This is the glowing splint. All right. In here we have oxygen. Okay. There is oxygen here, and then once you dip your glowing splint into this this conical flask that contains oxygen, it relights. This is how you know that there is oxygen in here. The flame will reappear. Okay. Then you know that. Then you know that there is oxygen in there. Is that okay? Any questions on that?
No.
Okay, very good. There is one slide here I missed. Let me go back a little bit. Okay, so this one says, unless you are oxygen, yes, I can live without you. So don't allow anyone to lie to you that I can't live without you. No, don't allow that. Unless they're oxygen, of course. But if they are not oxygen, you can live without them. All right, let's continue. Let's look at the preparation of oxygen from potassium chlorate. This one just is a little bit different. It involves the use of heat. So heat here is involved. We have a mixture of potassium chlorate and manganese oxide, of course, or is our catalyst. It's heated in a boiling tube, as showed. So here, we just have our mixture here of potassium chlorate and manganese oxide. We heat it, so there is heat involved. You see the Bunsen burner. And then our oxygen is formed and is collected again over water, just like we saw in the previous method. So the only thing here to remember is that there is heat involved when we are using potassium chlorate. Now heat, the reason why we use heat is to increase on the rate of the reaction, or is heat increases the rate of the reaction. Since we are dealing with potassium chlorate, it's a little bit, its particles require a little bit of heat to kick off the reaction or to speed up the reaction better, even though we have a catalyst involved. Heat also helps to facilitate this reaction. Any questions about this? Okay, if no questions, we can continue. All right. Let's continue. Here is the equation. We have our potassium chlorate. There is a catalyst involved that we saw, manganese oxide. It is decomposing to form potassium chloride and oxygen gas. Okay, here is the symbol equation or symbolic equation. Our potassium chlorate This is the formula of potassium chlorate. It is decomposing to form potassium chloride and the oxygen that we need. That's the reaction. Any questions about these reactions? No, these equations? Okay, let's continue. Industrial preparation of oxygen. Oxygen is manufactured on a large scale by fractional distillation of liquid air, like we talked about it previously. Air is passed through sodium hydroxide to remove carbon dioxide. So this is sort of an elimination method. You're removing all other components of air, just remain with oxygen. So first you'll pass your air through, you'll pass it through sodium hydroxide right there, okay? Sodium hydroxide. So the sodium hydroxide is to remove carbon dioxide. We know that carbon dioxide is also a component of air. And then through silica gel, okay, to dry the air. So this one does the drying, but also it removes the water vapor. By drying, we actually mean removing water vapor. So we know that water vapor is also another component that we find in air. So we remove it. So now we have water removed and carbon dioxide removed. Now we are remaining with the noble gases, right? How we remove those is to continue fractional distillation, and then we only remain with oxygen. The equation for removing carbon dioxide is here. Sodium hydroxide reacts with carbon dioxide to form sodium carbonate and water. So carbon dioxide is eliminated from the air that we have. And then the dry air containing nitrogen, oxygen, and the noble gases. Yes, I'd forgotten about nitrogen. So these are now the components remaining in our air that we have. Okay. These are the components remaining. We only need this oxygen. Okay. We are going to remove all these. We only need oxygen. We're going to remove noble gases and nitrogen. So this air is repeatedly compressed at a very high pressure and cooled into liquid air. All right, the liquid air appears blue because of the presence of oxygen. Fractional distillation of the liquid air is carried out to obtain oxygen, which boils at negative 183 degrees Celsius. So this is when you carry out your fractional distillation. Oxygen will be the first one to escape because all the rest have a higher boiling point. So we shall remain without oxygen and collect it after fractional distillation. All the rest we shall have eliminated. So that is the fractional distillation. That is how we make oxygen in large quantities or industrial preparation. So in case you are called upon by the Minister of Health, you know we have been having a lack of oxygen in many hospitals here in Uganda. In case you're called upon to give your knowledge about preparation of oxygen, do not give the laboratory preparation. Just give the industrial preparation because we'll need it in large quantities. Just tell them to fraction distillate air, give them the values, give them how to eliminate carbon dioxide, And then you'll have maybe oxygen in very, very large quantities. Tell them to store it in cylinders at very high pressures, just to make sure that you have it in large quantities.
Excuse me, sir.
So just in case, yeah.
Can the oxygen
Question?
that is prepared in the laboratory be used in hospitals?
Yes, 100%. It can be. It can be used. The thing is, for example, this one, the industrial prepared oxygen. The medical one has to be stored at a certain pressure, but also its release for a person to breathe it in, it should be at a certain pressure. Okay, oxygen as a molecule is the same all over. Okay, it doesn't change. The oxygen we make here is the same oxygen that is in air. It's the same oxygen that exists in nature. Okay, it doesn't change. There is no types of oxygen. Oxygen is the same. All right. The moment it is a molecule, it is the same. So it doesn't matter how you made it. Okay. You can make it in the laboratory. You can make it in the industrial process like this one. Store it at a certain pressure. Those cylinders that you normally see. And then while it is administered, for example, that one you've asked for the hospital, while it is being administered to the patient, it has to be released at a certain pressure not to kill the patient. In biology, you'll study that oxygen can also be poisonous. So too much oxygen is not good, right? So that's why it has to be released at a certain pressure for the patient to take in. Does that make sense?
Yes.
Okay, good. Any other questions?
Excuse me, sir.
All right. Yes, please.
The last statement, it says that oxygen which boils at negative 183 degrees Celsius. Isn't it supposed to be 183 degrees Celsius or negative 183 degrees Celsius?
It is negative 183 Celsius. That's a very good question. Now, here we are dealing with a gas, okay, a gas that has been turned into a liquid. When you turn a gas into a liquid, there are things that you need. First, you increase the pressure. You have seen it here, right?
Yes.
Right here, very high pressure. You increase the pressure. That's the first thing. And then you lower the temperature. Because we know that, for example, when you want to freeze water, you put it in a freezer, not so?
Yes.
It's the same thing that you do to turn a gas into a liquid. You lower the temperature, all right? So the temperature of liquid oxygen is in negatives, okay? That's the temperature of liquid oxygen. It is in negative. Therefore, when you increase that temperature a little bit, for example, if it was at negative 300, okay? Negative 300, okay? Let's say originally it was at this, negative 300, and then you increase the temperature to negative 183. At this temperature, negative 183, oxygen will start boiling seriously. It will start boiling, meaning it will start turning back into a gas. That's what it means. Okay, here at negative 300, let's say it was a liquid, and then you increase the temperature. Remember the negatives here. Once you lower the negative, it is increasing. Also, you've said that in math.
Yes.
Negative 300 is lower than negative 183. Okay. So once you increase to negative 183, then oxygen here will start boiling, meaning it will start turning into a gas. Okay. The boiling point is where you have a substance or a liquid turning from liquid to the gaseous phase. Okay. So That's the meaning of the negative here. Does that make sense?
Yes, sir.
Yeah. We know that water can become a solid at what temperature? 0 degrees Celsius, not so?
Yes.
Yes. But you can find ice that is at negative, let's say 10, okay? In some very cold countries, you find when the temperature for the day is like negative 10 degrees Celsius, and it is snowing and all that. Okay, so we have negative temperatures. That's the point I want to make. And oxygen boils at this negative temperature here. Does that make sense? Okay. Any other questions? Okay, good questions. Those were good questions. Let's continue. All right. You've heard of the phrase, hey, love is in the air. That is not true. Today we know that oxygen, nitrogen, and carbon dioxide are in the air. So you should not be lied to again that, hey, love is in the air, love is in the air. No, there's no love in the air. There is only, okay, of air. So now this will also help your question. This will help you see my answer the question about liquefaction. Sorry. The dry air containing nitrogen, oxygen, and up to 200 atmospheres. The compression of air takes place with evolution of heat. The word evolution means losing heat, meaning the temperatures are decreased. Once you see the word evolution of heat, just know the temperatures here are decreasing. So there is increase in pressure and evolution of heat involved when you're liquefying air, turning air into a and a cooling system. Again, you're seeing a cooling system. Okay. Every time you're dealing with liquefaction of a gas, you're dealing with decrease in temperature and increase in pressure. So in the process, the compressed mixture is cooled. The mixture is compressed and cooled repeatedly as the temperature gets lower and lower. So now this makes more sense, not so? And thereby the air is liquefied. So there are two things that we need to liquefy air: increase in pressure and then decrease in temperature. That's all. That's all we need to liquefy air. So that's how air is liquefied. I hope that helps to answer your question the more, and it helps your understanding.
Okay.
All right. Here is another one. People say you can't live without love. The thing is, you can't live without oxygen. Oxygen is more important. So you can live without love, but you can't live without oxygen. Once you're out of oxygen, you die. Okay. So let no one lie to you. All right. Properties of oxygen. We have the properties here. Oxygen. We shall deal with only physical properties. We shall start chemical properties next time. So it's odorless, tasteless, and colorless. It is slightly soluble or sparingly soluble in water. This is why it is collected over water. It's not entirely soluble. If it was entirely soluble in water, we wouldn't use water to collect it. But it is just sparingly soluble. It dissolves a little bit in water. So this is also why fish is able to breathe in water because there is some dissolved oxygen in water. Therefore, fish can survive. Yeah. It is approximately the same density as the air, as that of air. The density is almost the same. It is neutral, it's a neutral gas, therefore it has no effect on litmus paper. Okay. It's a neutral gas. Any questions?
What's the speaker?
Yes, please.
It's time for class.
It's time for what?
Skip to the class. Yes.
Arnold, please lower your volume. I mean, turn off the volume while you're speaking to other people. I see you've just joined. We're almost finishing.
The class almost getting done?
It's almost done, but you're welcome. You're welcome to attend until it ends.
Okay.
Yes. This is chemistry, S2. I hope you're in the right class.
Yes.
All right, good. So we're looking at oxygen and we are on the properties of oxygen. We have said oxygen is odorless, tasteless, and colorless. It is slightly soluble in water. This is why it's collected over water. It is approximately the same density as that of air, and it is neutral. Therefore, it has no effect on litmus paper. This is a conversation that I picked up between lungs and the heart. Okay, so the lungs said, we got something, we got you something. They were telling the heart, and the heart was like, oh, I love it. I am going to share it with everyone. And the gift was oxygen. Okay, this is how important oxygen is. Michael, you were telling us how it is taken into the lungs, the whole hemoglobin picks it up, takes it to the heart, and then the heart pumps it out to every part of the body. This is it right here. Okay, oxygen is an important gift that helps us to survive. It helps every living organism to survive. Okay, that's how important it is. Thank you for attending. I hope you subscribe and through some of the content that we have, and really helpful. Please consider to join Yaaka or subscribe to buy certain content in Educare. This PowerPoint with it and send you an activity to attempt. Thank you. Someone left their volume on. Thank you for attending. See you soon. I'll send you the activity in the WhatsApp group and also this PowerPoint. Well done. Any questions before you leave?
No.
No, sir.
All
Yes.
right. Have a nice day. There. Okay. All right. Bye.
Bye.